Alright, welcome to our introduction video about limits. Now unfortunately the topic of limits is really sort of legalistic and nitpicky, and there's a lot of details, a lot of rules you got to memorize. And I won't really put those in this video. Those are going to be in all the later videos about specific types of problems. So if you're in the limits chapter, you're going to probably want to watch all those videos because it'll cover all the different types of problems. In this video what we're going to do, rather than take a look at all the rules, is just going to talk about what are limits, what's the first step you should always take on every limits problem, just in case it turns out to be an easy one, and what the heck all this means. So number one, what is a limit problem? Well, we got this LIM, right? Stands for limit. It's got this little variable, like usually x, with an arrow and then a number. And the way that reads, and then we got a function here. So whatever is behind the limit function, all this stuff, that's like the function. So just like you take the sine of an angle, we're taking the limit of this function. So that's why if you translated this problem right now right here into English, it would read as the limit as x approaches 2, so meaning x is going closer and closer to 2, and then you notice we have the word of, and then x plus 1. So the function is what we're taking the limit of. And what this basically means is we're saying, hey, if you know anybody, and back in algebra 2 you could have found f of 2, right? You just plug in 2, you get a value for f, and that was really just your y coordinate. So if you just plug in 2, you get the point 2 comma 3, and that would just be a point that's on the graph, and you could also plug in f of 1, and you would have gotten that was 2. So you would have gotten all these points that were on the graph, and you could have graphed the thing by plugging in points like that, right? Well, it turns out that's kind of what we're doing with the limits. So what we're saying is, hey, you know, if you're approaching the x coordinate of 2, so if we were creeping along this graph this way towards x equals 2, which is right here, what does it look like the y coordinate is going to be when we get there? So as you're getting closer, you know, it's like 2.3, then 2.5, 2 1/4, 2 1/3, 2 1/16. We're getting really, really, really close, super close to x equals 2, but not quite there yet. What does it look like the y coordinate of this point right here is going to be? And you just look and say, well, duh, it looks like 3, right? Because this is the point 2 comma 3, and that's where we're obviously headed as we move along this graph. And of course, if I come from the left, same thing. If I was approaching from the left, it would look like, just as I get really close, it looks like, well, hey, we're going to land on 2 comma 3. That's where we're headed. So the limit is 3. And for a basic problem like this, we can actually just plug in. So that's why I wrote, hey, we can just plug in at the top. Because that's the first thing you should always try in limit problems. Just take whatever number they gave you here and plug it in for x, and that'll probably be the right answer. If you don't get something weird, but if you just get a number, it's right. So if we took 2 and plug it in here, we get 2 plus 1 is 3. And sure enough, the answer to this problem is 3. The limit as x approaches 2 of x plus 1 is 3. And the reason that was so simple is because this is just a line. You know, it's no big deal. We'll get into some wacky stuff later. Like later in this video, I'll show you some of the wacky types of problems we'll be looking at in later videos, but this is a really basic one. It was just a line, so yeah, the limit's just going to be that point. But the most basic way to solve all these problems is just plug in the number. So here's that same number again, plug in 2 for x, and we get 2 plus 1 is 3. Easy peasy. X approaching 0 on this one, all right. I don't know what that means, but hey, let's plug in 0 for x squared. We get 0 squared, which equals 0. Nice, the correct answer is 0. Limit as x approaches 3. Now in this one we've got 2 different x's, but that doesn't matter. We're just going to plug in 3 for each one of them. So we're going to get 3 minus 3 over 3 plus 2. Now you'll notice this is actually already getting a little bit funky because 3 minus 3 is 0. Uh-oh, we have 0 in a fraction. What does that mean? Well, it actually means it's 0 because the 0 is upstairs, and having a 0 upstairs is no big deal. Just like you'd have 1 half or 3 halves or 5 halves, you can have 0 halves, it would just be 0. So 0 over anything is 0, and that would just equal 0. So it turned out that even though that looked a little funky, got a little scary there for a second, plugging in still worked because we got 0 over a number. Same thing in this one, we can plug in 1 for x, so we'll get 1 plus 1 over 1 minus 1. And now we have another whoopsie daisy, there's a 0, right? This one is worse though because it's 2 divided by 0, and dividing by 0 is no good. It's undefined. I mean, 2 divided by 0 is undefined. It turns out that we're going to use a special word to describe this answer because it's a limit problem. So we're going to say the limit does not exist. So DNE stands for does not exist. You're saying, hey, the limit doesn't exist because you can't divide 2 by 0. And there would have been a vertical asymptote. If you graphed this thing, you would have gotten a crazy vertical asymptote at 1. And it would have gone like, zoom. So you're sort of like, as you approach 1, see how we're just like shooting off to infinity? Except infinity is not a number, so that just does not exist. So you just memorize, hey, if you ever have to divide by 0, the limit does not exist, it's undefined or whatever. So, I'm not going to work this problem right now, but suffice it to say, this is actually the same line we looked at in the previous slide, just a couple of minutes ago. But you'll notice what I did was, instead of just having a normal line that goes, no big deal, very easy to find the limit of, all of a sudden I said, you know what, let's take the point that was right here at 2, 3, the one we were using, and let's just move it up here, just to mess with your head, right? So it's kind of like a piecewise function from pre-calculus or something. The point is, this problem was made to mess with you, but we're going to go over the rules that apply to these graphing things. There's a few rules, and then I'll make it pretty plug and chug and pretty straightforward. Again, I don't want to get those rules now. I just want to show you that, hey, the way they're going to mess with you is they're going to give you fancy graphs and do stuff like taking a dot and putting it somewhere else, or putting an empty dot one place and then a closed dot somewhere else. Like, check out this next problem. Similar kind of thing. Once again, we have an open dot and a closed dot, except this time they're on the ends of functions. So we sort of start with an open dot and shoot left, start with a closed dot, shoot right. This should really remind you of piecewise functions in pre-calculus. But the moral of the story is that finding a limit as x approaches 1, it's going to be a little bit trickier, right? Because if we come from the right, we're approaching this point, but if we come from the left, we're approaching this point. So which one is the limit? I don't know. It's going to turn out that the left, we're going to have 2 limits. The left-handed limit is the one where we're coming from the left. The right-sided limit is the one coming from the right. And there'll just be some rules about when is it okay for them to miss, when do they have to hit, what's your answer if they miss, and there's like a left-sided limit and a right-sided limit, but they don't agree. You know, what do you do then? And ultimately, we'll even talk about continuity, which is basically talking about, hey, do they meet and stuff, and where's the open dots and closed dots. So all this crazy stuff I just showed you, the 2 graphing problems, that falls under graphical limits, or finding limits graphically. And that's a video later in this chapter, or maybe a couple of videos, not sure yet. And yeah, there you go. So the point is, funky graphing problems that look like piecewise functions, bummer. All right, the final type of problem, and the one that's going to get its own chapter because there's, you know, 5 or 6 different flavors of these, and I want to give a separate video to each type. But basically, it's like trig proofs. You know, just like trig proofs, there's sort of like 5 or 6 sort of general strategies that pretty much work for all proofs. You know, one or the other is going to work every time. Same thing here. We're going to have 5 or 6 strategies for dealing with limits. You know, we don't have a graph here. There's just crazy algebra, crazy functions, big fractions and stuff. We're just going to have 1 or 2 strategies for dealing with this. Now, you might be wondering, hey, Chris, you told me that what I should always do is just plug the number in. And I would say, you know what? Good catch. I'm glad you reminded me. So I'm going to try to plug it in 1. So what do I get? I get 1 minus 1 over 1 cubed, which is 1 minus 1 equals, oh, bad news. But now you might be telling me, hey, Chris, why is that bad? Because you told me that 0 over anything is 0. Oh, wait, but you also told me that anything divided by 0 is undefined. This is a problem. When you have 2 zeros, one over the other, we got a new word for that, indeterminate. And basically what that means is you're not done yet. There's some trickery and some math cookbooky type stuff and some plug and chug you could do to this thing to figure out what the limit actually is. Because 0 over 0, you might be thinking, oh, that just equals 1. Yeah, but it might equal 0, it might be 1/5, it might be equal 2/3, it might be 1,000. It's going to turn out, once we do some more math on this using the techniques from the next chapter, we'll get numbers for this. A lot of the times we'll get like a number out that's not 0 and not infinity or something. So that's when plug and chugging hurts, is not going to give you an answer. Same thing happens on this one. If we just plug in 0, because hey, that's the first thing we always try in limit problems, we're going to get sine of 0 over 0, which is again 0 over 0, which again is indeterminate. And it's going to turn out, I'm going to have a special video on this in the next chapter, because when you have a sine or cosine, there's one specific special rule you use for those. You'll just have to memorize. It won't make any sense, but hey, you know, anytime you see a sine or cosine, you'll think, oh, I got to use that one formula. So that's where we're headed with analytical limits. Just sort of like plugging and chugging, a lot of equations, no graphing to worry about. And that'll be the next chapter. All right, so that's limits in a nutshell. Get ready for all the fun action coming up. And just get ready to realize, you know what, you're going to have to memorize 6 or 8 different ways of doing problems. But once you learn what they are, and once I lay them out really straightforwardly, you'll recognize them and it won't be the end of the world. You can get on to the fun stuff of calculus, which is derivatives and integrals.